We're recording in 3, 2, 1. We are live this week, guys, because what we're doing, we're figuring out how cube maps, all this nice reflection-y stuff work, and frame buffers. We're doing a lot of new GL stuff today, which is somewhat interesting. Like this late into the term, we're finally like touching brand new GL objects. So there's a lot to do in this tute. So we're just gonna like dive straight into it. The first thing we're going to do is we're going to run the scene to see what it actually looks like. So here's our base scene. You guys, I'm sharing everything, so you should be able to see that window, right? Imagine I'm just seeing the previous job. It's a questionable. Can you guys see the screen? I'm pretty sure I set the right thing. Yeah, cool. So here we have a sphere, and here we have a wall, and here we have a black hole. And if we enter inside of this black ellipse, we get somewhere else. So here we have the first scientifically documented example of a wormhole. So that's pretty exciting. Here we have whatever this is. I'm not really sure. I guess it'd be a radio. Yeah. But obviously, we're going to be building up this thing to be doing more stuff. So the first thing we're going to do is we're going to take this very nice rainbow kind of rimmed. You kind of look at the rim, it's very blue, and then you like look somewhere else and it's red. We're going to take this sphere. We're going to add portals of this radio. That moment when I haven't actually played Portal before. So. Oh, topical. But we're going to add reflection to the sphere. Hopefully that'll make up for my clear lack of a culture. But we'll see. So let's go ahead and do it. Let's take this is a fairly complex program right now. So like you're definitely going to want to, if you want to use any of this stuff for assignment 3, you're definitely going to want to like spend some time. I can't put this right there. Spend some time studying this code because it's decently complex. But we're going to try and walk through it. So how are we doing things right now? Well, we have the usual time delta now to do our, frame limiting. But the secret is that we actually have 2 scenes that we're rendering for this. The exterior is obviously the outside of the sphere, and then the inside is the portal-ish room. Could I increase font size? Indeed, I could. Still, actually, I think yeah, there we go. Is that better? Sweet. Yeah, we have 2 scenes, and essentially we have this function, quick little function that I wrote, does some pretty nasty stuff, pretty gnarly hard coding of things. But essentially what we're doing is a very, very rudimentary collision detection, essentially is what's happening here. We're just checking to see if we crossed the portal boundary. And if we have, then we're inside, and if we haven't, then we're on the outside. And then this is the case, I think we're on the boundary. So yeah. And we're just basically figuring out which one needs to be active inside of our main function, which is what we're doing here. And then we're just rendering the active scene. So when we cross the portal, we switch whatever scene we're rendering. The scene, we don't have a scene struct the way we did before. Instead, our scene is just a node, the root node for whatever the hierarchy is that we have. So we're kind of like switching between these 2 nodes and their associated scene graphs to figure out like what scene that we're in. And that's kind of, we won't be looking at this node struct too much more, just kind of the internal stuff. Or of like, well, this texture specifically will be very, very useful. In fact, it will be so useful. That's the first thing we're going to modify because we need to go and load a cube map. And if you guys remember from cube maps, we'll go and take a look, see. The cube map, if I open up the implementation file, has 6 sides to a cube. Obviously, we have the right, left, top, bottom, front, and back. And if you look at those pictures, like you would have seen on LearnOpenGL, you have like 4 squares in a row here, and then on this like second from the left, we have an up and then a down. That's kind of how people draw out the cube maps. And unsurprisingly, the cube map textures do in fact need to be square. So that's important. But because what happens, you get big aspect ratio things if they're not square. But to work with the cube map, we actually kind of need all of the textures to be separate pictures. So it's actually kind of annoying to work with the flattened out cube scenario. Let's take a look, see what we're going to be reflecting statically. Well, not even statically, but we're going to be reflecting dynamically of our cube. Here we have this lovely little picture, and then on the bottom, front, left, right, and of course, the actual sky. And this comes straight from OpenGL. So there's nothing crazy going on there. But what we're going to do is we're going to create a new texture, cube map texture, for the very first time, and we're going to be plastering those textures onto the sides of the cube. We'll do that first. So let's go ahead and jump through it. This was meant to be a quote unquote helper function. I'm not going to use it. Let's put this up on its own line because we can fit it. We can fit it. Oh, and let's do it. So I mean, this part is not going to be particularly interesting. We're just going to create a new glue in. This is going to be a cube map. We'll get some nice swag using good old chicken, because you never know when you might need some chicken. And then we will bind this GL bind texture. And the new texture target now, for the very first time we're seeing, is called GL texture with an E, cube map, like that. And this is our base cube map texture target, our base cube map texture target. And from there, we just bind our cube map. Pretty simple, right? So even though we bound, shut up, sorry. I always forget to like silence that, and then I get the most notifications during shoots. Like it's actually kind of ridiculous. But once we've bound the cube map texture, the next thing that we need to do is we need to go and fill it with all of the different sides of the cube. So if you guys remember how to write loops, which might or may not be the case, then let's go ahead and make some for loop action. So we have our side, start from 0, naturally. And then how many sides are in the cube? The answer is 6 in this dimension. What we're going to do is we're going to be using GL text image 2D, GL text image 2D. And we're going to use a very special target. We're not going to be using the cube map target. Instead, we're going to be using a similar but unrelated. I'm used to writing ISD index, but it's not the side. So what we're going to be doing is, of course, we need to load the image of the texture. And we've seen how to do this before. We say chicken3421 image T is load image of our base path, which is this skybox place, but it gets passed to us, so we'll just reuse it. Actually, I believe if I do this, I won't get destroyed. So string path is base path, and then what I'm doing now is basically just string concatenation, but I don't want to get tons of like yellow warnings on the screen because it's just annoying. So we'll just add on to the string like this using appending, whatever the thing's called. We'll use suffixes, or if you speak English, suffixes, or whatever side we're looking at. So we'll start with the right one, and then the left, top, bottom, from back. This order is actually important for reasons I'll explain in a second. There we go. So we've got our image now. I'm going to figure out what the format is. What is it? GL int or GL enum, one of the two. This is something we've seen before, right? We're just going to be doing text image dot and channels. Is it 3? If it's 3, we know we've got an RGB formatted picture. Otherwise, if it's 4, we know that it's going to be RGB and A. Still making assumptions. There we go. Once we've got that, then like I said, we'll be using text image 2D one more time. And this new path, or not target, this new target we're going to be using, I like just completely botched my words there. It's going to be GL texture cube map, but you see we have these extra hash defines here. We have positive X, negative Z, negative X, negative Y, positive Y, positive Z. And what's interesting about these is we'll start with positive X. You might already have figured this out. If I go look at what this hash define is, what do you notice about these hash defines? It's 6, it's 5, 6, 7, 8, 9, 10. A is 10. These are in a row. So these are contiguous. You know what that means, right? It means that what we can do is we can just say the target will start off with our base, which is going to be positive x, and then we can just add on to that whatever the side's going to be, right? Because the side, I'll put it here. Because these are contiguous, if we just add on whatever side we're up to, then we'll get to the next one. So it goes positive x, positive y, positive z, negative z. And if you look at that, it's exactly the order that we've got here. Positive, negative, positive, negative, positive, negative, x, x, y, y, z, z. Nice and simple. So this text image 2D, we'll just fill it up with the rest of the stuff that we usually use. So we know we have first is the texture target, followed by netmap level, which is for us 0 because we're not using netmaps here. And then it's the format, and then it's the width, and then it's the height, and then it's 0, and then it's the format again because reasons. And then we have the type of the image data, and then we have the image data itself. Cool, and that's loaded. So we're going to set a few parameters for this texture. Because we're not using netmaps, we have to make sure that we set specifically the minification and magnification filters. We'll do that outside of the loop, actually. Inside of the loop, what we'll do is we'll just clean up this image. So to do that, we'll do COMP3421, delete image, text image. Just like that. And outside here, we'll start to set the parameters for this cube map. So GL texture cube map, GL texture mag filter. We'll set it to be GL linear. And the same thing for the min filter. And also, we need to set the wrap modes for ST and R, which is OpenGL's way of saying U, V, and W. I don't know, whatever the 3D texture coordinate would be. S is obviously U, T is V, R is whatever R is, the third dimension. And my question to you guys is, I'm going to set this to clamp to edge. Why am I setting these to clamp to edge? What do you guys think? Think about it for a little bit, consider it. I'll give you like 30 seconds. Why am I setting the clamp mode for the texture coordinates to basically stop at the edge? No wraparound. For what case? Goddamn COVID. So remember, to filter from a cube map, when we're grabbing the texture color, we get our position vector from wherever we are in the world, and we shoot it out and see where it hits on the cube map. What can happen if we do that? What if we've got two faces at a corner and we hit a vector right in between the middle of them? Or what if we've got, this is an edge. What if we have the corner and we hit right in the corner? We need to filter from there. And basically clamping to edge means we'll take whatever the side of the texture is for all three. And OpenGL has some nice like interpolation when you hit that edge case where you're literally on the edge case. And that's why we do this. Cool. So we made our cube map, but we're not using it. So let's go ahead and use it in our scene. Where is our scene exterior? Because we're applying it to the sphere, right? Because this outside sphere for realism, hypothetically. What we'll do, of course, is just set the sphere's texture to be. So I mean, just in the way the scene is set up, we just are keeping track of what each kind of node is. Loading. There's a lot of things with objects or .objs that Matt has created for us. Very kind of him. And we're just like setting the kind, the model that this thing is, and of course the texture. This portal texture, not important right now, but it will be. But for our spheres texture, we're going to set it to our cube map. Make cube map, and the base path is our skybox base path. Just like that. And then in our scene, obviously, we have everything set up like that. Right? So that's our cube map all set up. We still need to go, and we need to actually go and render with this. So we need to do that. To do that, we're going to make a few small modifications to our renderer that I should have made before, but I just remembered that I didn't. So let me just quickly do that. I don't think I need to change anything here. Just this. Basically, I'm just going to split up the model and the view matrices again. We'll call this one. What would you call this? What should I call this? Let's just grab this. Duplicate it there. This will be obviously just view. But for this one, I'll call this one model transform, MT, like that. We'll grab this and just duplicate it everywhere. What did I do? MT. Did I forget to copy the T? Let's go from there. Yeah, just all that. Oops. Yep, it's fine. MT. And then in the side of our render, we'll just fix up the function prototypes that are here as well. I think that was all the places. Yeah. If we look inside of our the shader now, which is going to be our shader for our vertex, let me just collapse it. So that's even better. Just stick it there. We have our model view like this. So what I'm going to do is I'm going to just cache what the result of this will be as a mat4 out here. We'll have our mat4, which will be U model view, but of course it will just be regular model view. And instead of it being model view, this will be model view. And you guessed it, it will in fact be U view times U. And every time I see model view, I'm going to replace it with model view. View model view, I'm going to replace it with this. Except for here, what I'm going to do here, which I'll explain in a second, so don't worry if I'm going a little too fast. We'll just replace that with here. And down here, that's it. I think that's all the changes. Let me just double check. U view, U view. Yep. Looks good. Open our fragment shader. And then inside of our renderer back here, we don't have just the model view uniform anymore. We obviously have the combined, or not combined, we have the opposite of combined. We have the split. So this one will be MT, this one is V. And I think everything else in this function is fine. Yeah. Same thing here. Is a very helpful to do to bind the cube map somewhere. I wonder where it could be. There we go. I think that's all the changes. Yep. So we did all of this literally just so we could split out inside of our shader here that it's changed. Huh. Just realized something. That's the fragment shader. Yeah, no, I haven't explained why we're doing it, which is the reason why it makes no sense. I just realized I made a doof. I made a mistake, or no. Luckily, I made a mistake now before things went bad. For this, for everything that's not reflective, I actually don't care about what this is. So let me undo that. This is just V times that. It's only for the portal, not the portal, the reflective one that I care about doing this. Cool. And let me just find the cube map here so we can get through and do what I actually want to explain. Sweet. Cool. So now let's take a look at the reflective vertex, right? So what's happening here? We're just we're passing the model, we're passing the view, we're passing the projection, as we've seen before in other tubes. We're then caching model view, so that way we kind of, do the model view projection transformation down here. But because what we're doing here is we need to shoot a vector out from wherever our object is onto his cube map texture to figure out where the reflection would be. And the way it works is what we do is we are doing this in view space. So we're taking our view, we're slicing our view, we're slicing the view matrix to a 3x3, timesing it by the normal of our sphere, which puts the thing into view space, right? And then what we're doing is we are, so here's inverse. Sorry, this bracket comes with this reflect. And we are reflecting this vector. Sorry, we're reflecting this vector around the view space normal. And what this is doing essentially is we are like what we're doing is, it's somewhat difficult to explain. But essentially what we're doing is we're shooting out a ray from the sphere to where it would hit on the cube map. Like it's our direction vector for where it is situated in the world. Doesn't really make sense. What I'm saying is that, like, depending on where we look at the cube map, depending on where we look at the sphere, right, we're going to see a different part of the reflection, which is going to depend on the normal of the sphere, and it's going to depend on when we are in the world, right? And the way that we kind of figure out what this would be is we do sort of what we do with specula, where we're reflecting what we see, the I vector, around the normal of the around the normal of the sphere. And essentially and then we're taking the inverse of that. And the reason why we take the inverse of the view matrix, which is already an inverse of the camera's perspective. And what that does is it essentially flips around. I have no idea what this math does. It was just given to me, if I'm honest with you. I understand it at a high level, but I don't understand the specifics of what this is. But essentially what's happening here is we are figuring out what the view direction will be on the cube map, so that way we get the right reflection. So if I rerun, well, first I have to actually sample from the cube map. And the way you do that is with another uniform. The sampler this time around is with the cube. We'll call this our cube map. Of course, it won't be this regular vector, it'll be our texture. Using our cube map and our text code. If we run this, hopefully nothing blows up, but it might. Oh, I missed one of the uniform things before. Where is that at? Somewhere. Model view. Did I call the matrix the wrong thing? Again, not the fragment shader. Model underscore view. I'm sorry. I have failed all of you. With but one underscore. Yeah, there we go. So as we see, this looks fucked. And the reason it looks fucked is because I forgot to flip the texture when we loaded it. Because OpenGL is backwards. Or is it upside down? It's hard to tell. There we go. So if we look at the sphere, right, it clearly has the reflection of the cube map that we created. So the reflection is depending on where we're looking at it from, and also the normal of the sphere. And so what this whole reflect, can I put it here? I don't have my cursor, so like I can't move the window around. Maybe if I do that. It's kind of difficult to do this. Hold on. Maybe it across a bit more. So we're reflecting what we're looking at around what the normal of the sphere will be in U space, kind of like what we do with the specular. And then by this, the U view is the view matrix, right? Which is already the inverse of the camera's local to world transform. By slicing this and inverting it again, this actually gives us the camera's local transform. And so what that you can think of it as is, and this is being multiplied together. This is still a 3x3 matrix, and then this is still just a regular old vector, right? When you reflect a vector, you get a vector. It's kind of like thinking we have our eye position, we have our sphere here, and we have our eye position. We're looking at our eye position this way, but then we're reflecting, so it's looking this way, and then we're looking at it from the position of the sphere. So really, we're kind of just getting this vector, but from the perspective of the sphere, not from the perspective of the camera. That's what's happening. And if you do that, and we imagine that the cube map is aligned with the axes in such a way that the left is the positive x-axis, the right is a positive x-axis, the left is the negative x-axis. This vector that we reflected from the perspective of the sphere is precisely the vector that we're going to use to sample from our cube map, which is a 3-dimensional vector. That's what's happening here. There, I figured it out. Does that kind of make sense, Hal? If you aren't sure, I don't know, stare at this till it makes sense, I suppose. You kind of have to like look at diagrams, which I don't have time to draw, unfortunately. But yeah. Anyway, let's keep going because time is a ticking, and I want to get onto showing the portal off. So the next thing we're going to do is we're going to try and render both of our things at once. We want to render the internal scene. We also want to render the external scene, and we want to be able to see the internal scene from outside, from the external scene through the portal. Let's go ahead and make this happen. To make it actually happen, we need some more stuff. And this is, in addition to our cube map, the next new thing, which is a frame buffer. Frame buffer underscore T. Do you guys remember what a frame buffer is from lectures? You can give me like a quick rundown of what a frame buffer is. Or who remembers maybe what it is. Crickets. Maybe you guys are typing, not sure. Well, in the interest of time, I will speed ahead. A frame buffer, right? We've been using a frame buffer this entire time. We were using it to draw to the screen, but we can also use frame buffers for user-defined purposes. One being, the primary one, is we want to render into a frame buffer to later be reused as texture. But naturally, we do actually need to create a frame buffer. So let's see how to do that. Inside of this make frame buffer, there are some key things. Actually, because this really is just like not that interesting, I'm not going to spend time typing it. What I'm going to do is I'm just going to grab the solution code and I'm going to like talk through everything that we're going to be doing with it and changing it, of course, because yeah, we all have our own style. So what I dislike is that. And we're going to fold some of this code, mainly like this kind of thing and this kind of thing. Well, kind of this kind of thing into chicken so you can like reuse it. But whilst I'm filling this in, let's talk about all the bits that we're doing. So the first thing we're obviously doing, generating a frame buffer, binding it the same way we do with every OpenGL thing, right? We do this with textures, we do this with VAOs, VBOs, everything. Frame buffers are interesting in that they're kind of like a VAO, in that a frame buffer by itself is not complete. For a frame buffer to actually be complete, you need to attach some things to it. So right now, one of the things that we can attach is actually a texture. Now, the other thing that we can attach is this thing called a render buffer, which is also new. And a render buffer is a lot like let me just fill in these variable things and return at the end. So a render buffer is a lot like a texture, but a render buffer is specifically optimized to not be filtered from, And so if you think about it, this render buffers in general, they can hold color, they can hold depth, they can hold stencil information. We aren't using any stencil information, so it's not important. We are using, however, depth, which I'll explain this line in a second. But a render buffer is specifically optimized to not be filtered from, which is different from a texture. So a texture internally has like data structures and algorithms to help with the whole like interpolation, rendering kind of stuff. A render buffer is like you render into it and then you just reuse what you got. You don't like try to interpolate values between. So it's a different data structure under the hood. That's why it's optimized just for rendering. Hence why it's called a render buffer. In our case here, we're using an actual texture as the color information. And for our depth buffer, we're just going to be using this render buffer. And a render buffer, being another OpenGL object, is created the same way. You generate one or n many to an array, and then you bind it to this special target called the render buffer target, of which there is only one. So that's pretty easy. And then you give it storage, just like you give a texture storage, give a VBO storage, all that stuff. The storage format is interesting, and there's a whole bunch of these. So if I just like kind of quick back a little bit, you can see you can create a depth buffer, which allocates 24 bits to the depth, which is all you'd really need, 24 bits for X, Y, and Z information to be interesting. 8 bits for stencil. You could use 32-bit float, and then 8-bit for stencil. There's more stuff. We're going to be using this kind of breakdown. So 75% of the storage will be for depth information. The other 25% will be for stencil, which again, we aren't using, but it's just kind of a standard thing. Render buffers are specifically designed to be used with frame buffer objects, which is why when we create our frame buffer object, the attachments we use, which specifically are our color information, taking the width and the height of the frame buffer object. This render buffer also takes the width and the height. And then this is sort of the interesting bit right here. So these are the so-called attachments. You can have tons of different color attachments, which means you can render to lots of different textures in a frame buffer object. Also, you can either use an RBO specifically for depth, specifically for stencil, and then obviously we have the combination of the two, which matches our storage here. And so the color attachment is for color information. When we render our scene that's into this frame buffer object that's not going to the screen, we have this is basically our color buffer, right? Remember how we do GL clear color buffer stuff? This is the color buffer that we're setting here. And we talk about the depth buffer and all that stuff. Well, that happens here as well. So this is like the depth buffer / stencil, and then this is the color buffer. So we just have to set those essentially. The arguments here are pretty obvious. It's like, which frame buffer target are we doing? There's just one, the GL frame buffer. What attachment are we binding this texture for? The first color attachment. What do we expect FBuff texture to be? A texture 2D, which it is. And then this is the mip-map level, which is 0 because we're using mip-maps. And then for this one, the frame buffer, again, same frame buffer as before. Depth stencil, that's what it is. We're taking this RBO, this render buffer object, we're expecting to be bound to this target, which is kind of just for symmetry with this. This is like the only target, so of course it'd be that. And then we just reset the state and return the frame buffer object. And there you go, that's our frame buffer object, just like that. So here we have a completely new frame buffer to render into. So let's add it to our scene. Where is it? If we go back to main, we have some little places we can put stuff in. We go to create our frame buffer, obviously. So let's create it. Frame buffer T. FBuff equals make frame buffer. So the frame buffer, like we said in the lectures, doesn't necessarily have to correspond 1-to-1 with what is on the window. In that case, you would have to set GL viewport. Like if I had a frame buffer of a different size, at some point before I make the frame buffer, at some point before I render the frame buffer with that frame buffer, I would have to set the viewport size with GL viewport, right? But our frame buffer in this case is going to be the same size as the window for reasons we'll talk about in a second. So when we make the frame buffer, we only need to pass in what the window dimensions are, and we won't need to set the viewport because when we create our window, the viewport will automatically be set to this width and this height. And because this shares the same width and the height, we don't need to do anything, which is fine. But in general, you would. And if you do Xavier's activities on in the OpenGL practice, then you would, because those are different sizes. Now our portal texture here, which is 0. Now we're obviously, let me explain how the portals work in general. So the portals are a bit of a hack, again, like everything. It's not that we're going to be looking through to the other scene from the portal, kind of like how the Duke Nukem thing worked. Instead, what we're going to be doing is we're just going to be applying the other scene of whatever we're in as a texture to the portal. And we're going to be doing some trickery with texture coordinates to make it look like we're peering through it, but it's flat. It won't actually be the true thing. And so obviously the portal texture that we're going to be set will depend on our rendering of the other scene with our camera. And that's exactly what we set inside of our frame buffer. So this will just be the texture. So once we've got that, we just need to go ahead and render with it. And the way we do that is we need to, even though we've created the frame buffer, we haven't actually drawn with it. So we need to go ahead and draw with it. And we set that by saying GL draw buffers. And the way that we, oh, I'm forgetting the line of code which gives us. 1 second, let me just double check on that. Close your eyes. Okay, never mind. Sorry, what I was getting confused here was something that we do in OpenGL 4.0, 4.6. We don't do that here. All we need to do is just bind the frame buffer here. Of course, once we're done, we set it back to what it originally was. And here we're just going to render our scene. But of course, instead of it being the active scene, we will be doing the inactive scene, just like that. And where else do we need to do stuff? It should be fine, I think. Let me just double check the scene is okay. I think everything's fine. And the render should be fine too. Yeah. You know what? Screw it. Let's just try and run it, see what happens. Will we blow up? We did not blow up. Look at that. Look at it. Look at it. It's amazing. It's kind of not great. It's kind of broken. Not gonna lie. It's kind of broken. But look at it. It's amazing. So what's happening here, right? Imagine that we don't have this outside scene being drawn right now. Instead, imagine we're in the inside scene, but from super far away with our camera. That is what is being rendered into our frame buffer object. And then we're just basically applying what we see to this portal as we move the camera around, it moves with us because it's like this outside scene doesn't exist and we're only looking at the inside scene. But I mean, I don't know. I think Valve might have one up just a little bit, but I'm not sure. This kind of really shows the man behind the curtain though, because you can see this truly is just a flat texture. It's not that we're looking inside at all. So clearly this isn't going to work, right? We need to do more stuff. But if we go through, then we're inside. Same thing happens on the outside. It's yeah, kind of fun. So what's happening here? Well, what's happening is that we're just taking our entire texture that we created from our first rendering to the off-scene buffer, and we're just applying that flatly to the portal. And that's not, well, it's not correct. What we really want to have happen is we're still looking at our scene with our camera, but we only want, imagine we have our camera and we're shooting a ray through to the portal. And we're seeing kind of what perspective we see with the ray. We want to take that part of the texture that we create. Now, we're not actually going to be shooting a ray. We're going to be doing something slightly more interesting. And the place that we do this is going to be inside of portal.dirt. So we're going to do a little bit of maths right now. So if we look at GL position, right? GL position is a normalized device coordinates, aka screen space. It's basically in screen space, except it just hasn't been flattened down yet. It's a cube, but whatever the XY coordinates will be, once in GL position will remain at the end. All that will happen is that after clipping, the Z will be collapsed down by a perspective transform. Now, imagine that again, we have our scene, right? Imagine we have our scene. This won't work anymore because I just removed from the shader. Yeah, let me just put this back. Pretend we're looking at our scene again from way away. And instead of seeing the outside scene, actually, you don't even have to pretend we're looking at the other scene. Pretend we're looking at our outside scene just like this. What we're seeing right now is the scene rendered from the camera and then transformed into screen space. And then we're seeing essentially a texture of our scene applied to the screen. That's kind of conceptually what's happening here. Well, if we take these screen space coordinates, and then what we do is we think about the fragments that make up the portal. What we want to do is we want to take the fragments that make up this portal, and we want to see sort of which slice that cuts out of our screen space rendered scene. So we know our texture coordinates, whatever they're going to be, are going to be something to do with screen space. So we can start with that. That's a good place to start. So we'll take GL position. Now remember, texture coordinates only go in the U and V direction. So we'll take GL position. Dot XY. And what we're going to do is we're going to say, okay, whatever fragment this is going to eventually become, let's say that is the UV, and which makes sense, right? If we look at the fragment, if we look at the portal from a side-on view, we only see some of the fragments, and we're going to imagine that those fragments that we see become the UV coordinates on our texture map. Now, we can't simply just use GL position.xy because we still have that perspective transform that exists. So we need to go ahead and add our perspective transform in ourselves, which is in the W. This is all OpenGL does after it's done clipping. It just does literally this exact equation. So let's see if that's any improvement. It was not. What did I do? Field selection. Oh, who would win? 24-year-old or one typo? Hint, it was the typo. Okay. Something's happened. Well, now we don't see this thing like this, but it's still kind of, I mean, I don't know, still kind of broken. But you can see, right? We're kind of getting there. We're getting this weird, like wavy quadrant effect. So I don't know. This is like psychedelic. So what are we going to do here? Well, there's one thing that I forgot to mention, or rather, I purposely left off, which you may have noticed by me not talking about this. So what you might have remembered is that the OpenGL will interpolate all attributes from the vertex to the fragment shader, and we'll do a linear interpolation. What we've neglected to tell you up until this point is that it will also do a perspective interpolation for you. So even if you look at something flat side on, it will do a perspective transform for you in addition to the basic linear interpolation. But we don't want that for our v-text coordinate in this case. And the reason for that is because this is already, we're doing text coordinates already in screen space. We don't need this to happen. And if you want to turn this off, then what you do is you just go to here and you add one of these interpolation qualifiers. And we're saying we don't want you to add a perspective transform. And if you want to read more about this, you can find it on the OpenGL wiki. There's basically just a hyperbolic, there's another matrix that everything gets multiplied by, essentially, to do the perspective, another perspective transform for things like this, for attributes as they are moved about the shader stages. So I'm not going to dwell on it, but you just kind of need to accept this as gospel. I know it's hard to accept things without knowing how they work. And now if we reload this, what do we get? Well, I mean, you can see the perspective transform is gone. So now when we look at it side on, we get just straight lines instead of it being wavy. That's how you know the transform has been nulled out. But I mean, this is somewhat interesting. So what's happening now? You guys remember the NDC coordinates? The NDC coordinate space, where'd it go from? It goes from -1, 1, -1, 1 in the X, Y, X, X, Y, Y, right? But our UCs go from 0 to 1. So we're so close, But of course, we need to just do another coordinate transform here just to convert these to, well, TC space. I think what we need to do is do 0.5 times, what do we need to do? I forget what the transform is. Oh, I was close. Yeah. I mean, I probably should have thought about this in my mind, honestly. So it's so obvious that it would be whatever this is. Yeah. The classic scale and shift, right? Scale and shift. So if it goes from -1 to 1, by halving it, it now goes between -0.5 and positive 0.5, and then we just add 0.5 to both. Of course, that would transform it. But I'm stupid, so what are you going to do? So if we now run this, what do we get? Ah, success! Look at it. It's a portal. It's still kind of broken because we have this blue rim on the inside because we can see the other side of the portal, essentially. But look at it. It's amazing. And what's even funnier is that this is fake. It's not that we're seeing through to the other side of the room. What, of course, is actually happening is that we are just rendering the scene off screen, and then we're applying what we would have seen as a texture. And look at it. It's kind of funny. Now, if we walk through, it's amazing. But unfortunately, we aren't fully there yet. And what's happening right now? Well, if you think about it, here we are in the exterior world, right? If we go over here and we turn around, we see this brick wall. Now, if you think about what I said before, we're still rendering both scenes. We're just rendering the scenes off screen as if the other scene doesn't exist. So right now we see this inside screen, but on the other side, we're rendering the outside scene as if we are, well, not here. We're rendering the outside scene as if we're here off screen. That's why we see this wall. So when we go inside, when we go inside, it's kind of funny, right? Like it's not a true portal because like you can't go in from the back. It kind of breaks. Like you're coming from here. We're seeing the back side of the wall essentially is what's happening. So to fix this, what we would need to do is we would need to say, okay, when we're out here, let's draw everything. But when we're inside of here, let's clip everything that's behind this wall so that we don't see it, essentially. Now we can't just do that easily because OpenGL only runs a single clipping system. And that happens when we take our points here, take our points GL position. Like I said before, this translates our position into NDC, normalized device coordinates, which is a cube. It's actually called the canonical view volume, but whatever. And then OpenGL will clip whatever is above, below, to the left, to the right, to the front, to the back for us. But that's not going to be good enough when we're doing off-screen rendering because OpenGL doesn't know that we're actually rendering two scenes, essentially. So we need to do this ourselves. And unfortunately, I'm out of time. So we're not going to be doing that today. But what we would do is, let me just jump over to the basic idea. It's not too hard to understand conceptually. What we do is where is it? Here. We're going to define a new clipping plane. And this clipping plane uses, some basic linear algebra about the definition of the plane. You take a point on the plane, you take a normal to the plane. From that, you can derive the equation of the plane by doing, what's the equation of the plane? It's like v dot n dot p or something like that. The equation of a plane in, point normal form, I think. That's the equation that's being used. Point normal form of planes. It's p plus b dot n. That's where it is. Where is it? Yeah, that's what it is. It's n dot p times p, where this p is a vector, equals 0. And from that, if you expand it, you can get the coefficients of the plane, which is usually in terms of an x, a y, and a z. This equation is kind of backwards because this has done it in terms of translations. We actually would want the full coefficients, which in this case would be 3y, 1x, -7 for the z, and then the d coefficient for the constant would be -9 plus 28, which would be 19. So the equation for this plane would be 1x plus 3y. Oh, I forgot the 2 there, so it'd be what, 21. So it'd be 1x, 3y, -7z plus 21 equals 0. And that's the equation of this plane. And if you had the equation of the plane, then you would come back, you would pass the equation of the plane to the renderer, to the shader, sorry, inside of our vertex shader. And then what you would have to do, so we are passing the clip plane here as a vector, and this vector is in a position. This vector is a vector of coefficients. So the first element would be the x coefficient, then y, then z, then the constant coefficient. And what you do is you can manually calculate the clipping distance, which is a signed value. Actually, I could probably, no, it's 3 p.m., so I won't. So this will be in the solution, which will be released in 2 days. So you can play around with it then. But basically, once you clip out the back of the wall, then you'll be able to see back into the exterior. So let me just get reset this because we're done basically. Actually, what I'll do is, yeah, I'll get reset. All right. Actually, no, I will do this because I'm lazy. Grab that, just do a copy to like. No. What I'm doing is just a little optimization. Yep. I don't know how to use git stash, is kind of my problem. If we run this to see what the actual solution would be, it'll be everything we saw today. But when you go through, if you look behind, because we have this extra clipping plane, it's actually kind of bugged, which is somewhat funny. We are clipping the back of the wall, and it seems we're also clipping slightly too far on the side as well, which is, whoops, there we go, like that. So you can see what's happening is that anything that's on the back of the wall is being cut off, but it looks like it's also cutting off there as well. I'm not sure why, but yeah. Anyway, guys, that's the end of today's today's Tute, not lecture. So let me stop sharing. Like I said, that if you want to stay or come back after 4, I might answer some questions on assignment because people seem to want that. So that'll be it. And if you don't want to stay, that's all good. So I'll see you guys next week, okay? For our very last Tute. Will it be ray tracing? I don't know. No, it won't be.